Hi, welcome to free body diagrams. Free body diagrams are just a simple way to represent problems that we're going to try to figure out in physics. So let's get started. Let's start with a question that may be familiar to you because it appeared on your pre-concept test that you took earlier in the course. If an object is at rest, then there are no forces acting on it. Well, let's think about this. If it's at rest, it's not moving. It certainly makes sense that it's possible that there are no forces acting on it. But I think actually we can think of situations where there are forces acting on an object and yet it still is at rest and not moving. Let's consider somebody sitting in a chair. I think I may have mentioned I can't draw, so I grabbed this picture here. Now, I think we're missing something here from Mr. Very Straight Back Guy, and that is, what is the chair sitting on? Do we really care? Possibly. I don't know. Why don't we put in some ground? So this would be the floor, let's say. Okay, so the person's sitting motionless. Are there any forces acting on him? Well, probably. I didn't specify, but unless I tell you otherwise, let's assume that we're sitting on the surface of the Earth. So yes, we are on Earth. If we're on Earth, what do we always have acting on us? And as we get older and older, it seems to be stronger and stronger, although that's not really true. Gravity. So I'm going to use an arrow. Remember what arrows represent? Vectors. So you're right. A force due to gravity is a vector. Big F for force, and then a little subscript G, usually for gravity. All right, so anything else? Well, let's see. If there were just gravity acting on the body, what should happen? It should start falling. This is clearly not happening. It doesn't happen as I'm sitting in my chair right now. What else is acting on this person? There must be some other force to counterbalance that. That has to be exactly opposite. And we call this a normal force. Normal not as not unusual, but rather normal in a mathematical sense. That means perpendicular to a surface. So if this person is sitting in the chair, the normal force pushes upwards, perpendicular to the surface he's sitting on. Well, he's not moving. He's not moving at all. He's not accelerating. So overall, that means something is zero. What is that? The total force. So we would say that and we call that the net force, sort of like your actual, what you've not grossed, but what you netted. Let's say if we're talking about money. So in this case, we would say F net. And that just means add all forces equals, well, we've got gravity and we've got the normal force. So how does that work? Interesting. So let's think about this. So let's put a few numbers on this. I'm going to go ahead and let's go ahead and start again with a fresh slide here. So I'm going to indicate that force of gravity. Let's say that I weigh, I don't know, 1,000 newtons, let's say. Pushing downward. Now we know because F net equals 0, I'll write that up again, that bears saying, which then means that the force of gravity is exactly counteracted by the normal force. They have to be the same. But they can't be. If I added 1,000 and 1,000 newtons, that would be 2,000 newtons. And something, I've got to be zooming along somewhere. That's not true. So remember our old friends, the absolute value bars. It must mean that the absolute values are the same, or really what's more useful is that the force of gravity has to be the same size, but remember these are vectors, they have a direction, and the opposite direction. How do we say opposite direction in math? We say it's the negative. So if we're going to define up as being positive, let's say then gravity is going to be a force of negative 1,000 newtons. And then we also have the normal force. And if that's going up, and we said, okay, let's call it a positive, that's going to be positive 1,000 newtons. You usually don't write the plus sign, but I'm just using it to make a point. So of course, if I add 1,000 newtons to negative 1,000 newtons, the result, of course, is that F net equals 0. And that's exactly what we have. This is a little ugly, so let me show you what a true full-on free body diagram looks like. Basically, objects, no matter if they're people, pelicans, pizzas, or cars, are a rectangle. And then we draw all the forces acting on it. So if this is the person in the chair, I'll try to label them person, oops, S, sitting. We have, in the simplest case, we have Fg negative 1,000 newtons, Fn normal force equals positive 1,000 newtons. And this time I'm going to not bother writing the positive sign. So what is the resultant? Remember the word from our vectors? So the resultant of these two vectors is that we have F net. Let's remember everything added together. Fg plus F normal. That equals 1,000 newtons plus a negative 1,000 newtons, running out of space here, equals 0 newtons. So, back to our statement up here. Not necessary, so it's not true in all cases, so then we've got to actually say this one's false. There could be, but what has to be true? But, and this is a big but, so to speak, F net must equal 0. And that's the big difference. There can be forces, but as long as they all balance out, their object is going to definitely be at rest.